Hello, Algebra 2. Today we are going to look at what's called quadratic regression, and we're actually going to use decimals in order to help us to write quadratic equations that represent different relationships. We're also going to look at what is correlation coefficient and what that tells us about the data. In your statistics future, you're going to learn a little bit more about this and the importance, and you're going to use regression a little bit more. We have done linear regression, and we have in our linear regression assignment and lesson gone through similar steps as we will for quadratic. So what we're going to do in decimals, and this is decimals is the main tool that we're going to use. It's the only one I'm going to show. However, if you want to know how to do it on your graphing calculator, I'll scroll down so you can either pause the video or take a picture, a screenshot of those steps if you want to know how to use your graphing calculator for this. For our use, we're going to be using decimals. So we're going to add a table. We're going to enter all the input and output values. And then we're going to type in our second field the standard form of a quadratic. And we're going to go through that with a couple examples. Now, this is your opportunity. If you do want to see the directions for graphing calculator, this is the process that you can go through for a graphing calculator for the steps. You're going to go into stats and enter that. Second, you're gonna type in all of your data, go through this step, and then lastly, you're going to go through this step in order to make it through the A, B, and C, which we need for a quadratic function in standard form. So again, if you want to take a screenshot that, we have got the steps there, but we are going to use decimals. So for decimals, we're going to go through a couple problems here using decimals so that you have a couple examples done fully for you, and then your practice today, you're going to do some more. So let's go ahead and make sure we've got decimals up here. So here we've got our first table. What we're going to do is we're going to determine the equation that represents this table. We're also going to find and interpret the correlation coefficient. And once we have that on decimals, I'll show you where that is and what that tells us about this data and the model, the equation or model that this data represents. So let's go ahead. We're going to add item. We're going to add a table. This is also the first step that we did when we did linear programming or linear regression. So here we're going to enter all of those. So we've got 0 and -9, 1 and -4, 2, 5, 3, 18, 4, 35, 5, 56. I'm going to zoom out just a little bit just to show you that this is indeed, it has a curve to it. It is not looking linear. It does look parabolic. It's kind of like half a parabola, and that's what we can find sometimes, often for some of our situations because maybe something's dropped or something, in this case, it's going up. So something has a 0 but negative don't make sense. So maybe time or something like that is at play here. All right, so that's our first part. We're going to enter that table. In 2, we're going to type in our equation for a standard form of an equation. So with that, we want y, and you can also use this. Let me go back to what I just did. So here, I'm going into the keypad, and we want this to be an estimation. Actually, I need a y sub 1. Ax squared, except anytime we have an x or y, we're going to sub 1. And we're going to square that plus bx. And again, whenever we have an x or y, we'll have to sub 1 plus c. So notice y equals ax squared plus bx plus c is the standard form of a quadratic. This is one of the 3 forms that we have in this section on quadratics and our last section on quadratics. So that'll help us remember what to type in. All right, so we've got some stuff here. We've got an a a B and a C. Well, that tells us what our A, B, and C should be when we write our equation. So let's go ahead and do that. Going back over to the question we have, our A is 2, our B is 3, and our C is -9. So the equation that represents this data based on what Desmos gave us is y equals ax squared plus bx plus c. Oops, I wrote b when I said it, but we want to put the value in for b, which is 3. Plus a -9 is -9, so I just simplified that. All right, the correlation coefficient. The correlation coefficient when we're talking about a quadratic is an r squared. Now, when we looked at linear regression, we looked for that r. Here we're going to look for r squared. The closer the correlation coefficient is to 1 or -1, the absolute value of 1, the better that data represents, or the better the model or the equation represents that data, which tells us that if we were to use it to predict something, that would be a good equation to use. It represents that data well, and we could have some confidence that our equation that we had, or the model is what it's often called, is a good representation and it can be used to predict. So here our correlation coefficient is 1. So this is highly accurate. These points are actually all in the same parabola. So the correlation coefficient, the r squared, is 1. So that is our find part. We're doing both. Find, we found it. And then we are also asked to interpret. So that is a second part that we're going to have to do when we have that direction. So interpret means, well, what does that mean? That means that the model, which is what the term we use for the equation that we write when we have this type of application type situation, the model represents the data well. And if we use this, it could be used to predict something with great confidence, because that correlation coefficient is 1. If you can't get any closer to 1 than that, we can predict with with great confidence, I'm going to say. All right, well, there we go. So if we used this model to determine something, we could do that with great confidence. All right, let's look at one more. Here's our next table. A garden hose sprays a stream of water across a lawn. The table shows the approximate height of the stream at various distances from the nozzle. We're going to find the quadratic equation or model that best fits this. We're going to determine and interpret the correlation coefficient, and then we're also going to figure out what's the approximate height of the water if you stand 2 and 8 tenths from the nozzle. All right, so let's go through those steps again, just so you can see each of those pieces for Desmos once more. So again, if we want to do a quadratic regression, we're going to add a table, and we're going to input all of the input-output, or all of the x's and y's, all of the distances and heights in this situation. So 0, 1, 1, 1 and 6 tenths, 2, 2 and 1 tenth, 2 and 5 tenths, 2, 3, 1 and 6 tenths, 3 and 5 tenths, and 1 and 3 tenths. Now, when you look at that, this is definitely looking like a parabola a little bit more than a line. One would argue this definitely is more quadratic than linear. So we should be able to see that this does look like it is either part of a parabola, or in this case, it looks like if we were to sketch a parabola, we could sketch that entire parabola. All right, so now the second part, we want Desmos to give us what is the estimated A, B, and C for this data. So again, we're going to enter Y sub 1, arrow out of there, approximately equal to AX sub 1, arrow out of there. It's a quadratic, so this is squared, AX squared, plus BX. X's and Y's need a sub 1, arrow out of there, plus C. All right. So here we've got an A, a B, and a C, and we're going to use that to do part A here, find the quadratic equation of best fit. So let's go back to that page, and we're going to write that again in standard form. So Y equals A. I'm going to round it in the nearest hundredth because I really don't want to make this more laborious. So I'm going to round to the nearest hundredth. So AX squared plus B plus C. Again, I rounded the nearest hundredth. If you're not directed at how to round, you certainly could round to a different decimal point. All right, next part, to determine and interpret the correlation coefficient. So let's determine that. What is that correlation coefficient? That is our R squared. So about 94 hundredths is the correlation coefficient. Is that close to 1? Absolutely it is. So with our interpretation, we're going to state in some form that it represents the data, and we can use this model with confidence to answer questions related to the stream of this garden hose. So the model or the equation represents the data well. So it provides confidence, or we can use this model need a little bit more space here. So it provides confidence when used. Or we can use this with confidence. If you were asked something about the distance or the height of this garden hose, we could answer it and say we could test it out and it should be pretty accurate. All right, now we're going to find the model to determine if you stand 2 8 meters from the nozzle, what would the height be? So let's go ahead and look at what part, what variable, what input or output are we talking about? So here we're looking for if you stand. So if you're standing away from something, we're looking for the distance. Oh, and this should be feet. Make that the correct unit. All right, so this is the input or the x of our function. So we could use this function we found in A and actually do the calculation. We also could come over to our graph and we could estimate where those are. So if we look for where x is about 2.8 on this function, x is about 2.8, well, about right there. Do you notice that x is 2.8 when y is about 1.79? So 2 8/10 gives us an output of 1 7/9. In some of your assignment, you're going to be asked to find an input for an output. So if we were asked to determine what is the distance away from the nozzle when the stream hits a height of 4 feet away from the nozzle, we would go ahead and we would find, well, in this case, I guess we don't have a height of 4, do we? Maybe a height of, let's say a height of 1. We could use our graph and find where is y1, and then from there, estimate what our x would be. So you could use your graph to estimate either x's or y's. If we are asked to estimate or to approximate using a model, and we have the input given to us, which is what we have in part C, you can substitute into the equation and simplify. If you are given the y or the output, I would encourage you to use the graph because we haven't really gone through fully how to solve quadratic equations when we don't know an x. But we can look at a graph and determine what is x when y is something. All right, so again, you can use either one of those methods in order to answer these questions. You can either use your graph or you can use your calculation. So we've got about, let's see, I'm going to give myself a little more space. The height is approximately, I think we found 1.79. Let's go ahead and check by calculations as well. If you calculate that, do you agree with what our graph was showing? So an x is 2.8. About 1.79. Is what you should get. All right, on your practice today, you do have more problems like this. Once you are done, I would like you to check the key. Of course, you can log on to Zoom or email me if you have any questions.